Hello, everyone. So today we're going to be talking about the temperature dependence of enthalpy. So to do this, we're going to be making use of isobaric heat capacities. So just as a quick review, it's important to remember that the change in enthalpy is essentially going to be equivalent to the change or instantaneous amount of heat under isobaric conditions that's being transferred. So we're going to see uh, very analogous systems to what we saw for internal energy and isochoric conditions. So similarly, because the change under isobaric conditions, the change in enthalpy is equal to the change in heat, we can thus make an analogy that any change in enthalpy is simply due to any sort of temperature difference. And as a result, we can go ahead and expand this into a calculus-laden form where we have the change in heat with temperature being related to the change in heat with temperature under isobaric conditions. The isobaric conditions being the key part here. And we go ahead and label this first derivative as our isobaric heat capacity. So again, what we see here is that the isobaric heat capacity is going to be a relationship in between the change in enthalpy of a system and its internal temperature, which again can be thought of as a ratio in between the change in the kinetic energy or linear linear energy of the system and the actual total enthalpy of the system. So again, we see a relationship in between the change in enthalpy, the isobaric heat that it takes to get this change in enthalpy, and the change in temperature, with again, the isobaric heat capacity acting as a proportionality constant. And again, we can think of this in more verbal terms as enthalpy being a measure of how much heat it takes to require an object at constant pressure. And again, this is one of the reasons we really love enthalpy to begin with, is because enthalpy is going to be much more representative of a lot of the objects we tend to work with, because it turns out most of the time I'm working under isobaric conditions. And it turns out that my pressure is typically about 1 atmosphere because I usually have a container open to the atmosphere, just the way the world works. However, it is worth noting that we now have our isobaric heat capacity, but it could be really useful to have some sort of comparison to our isochoric heat capacity. So again, our isochoric heat capacity is related to the change in internal energy, and our isobaric heat capacity is related to the change in enthalpy. So if I want to go ahead and relate my two heat capacities, I'm going to want to try and relate my two properties, enthalpy and internal energy. And as we've shown previously, this is going to be related by the change of the pressure and the volume of the system. Now, you can go ahead and solve this system for kind of an abstract material, but it turns out that this PV term becomes rather complicated for a lot of materials. So instead, we're going to do our usual and focus in on an ideal gas to see what sort of insights we can get from our system. And what we see is that for an ideal gas, I can go ahead and replace my PV term with nRT. Well, this is actually quite useful because we're mostly dealing with a closed system. So N and our constant R can come out in front of the derivative. And what we have is the enthalpy being related to the change in internal energy and the change in temperature with a constant prefactor on the temperature term. So what we can then do is to get everybody with respect to a change in temperature, I can more or less multiply by 1 and bring in a dt term for both my internal energy and my enthalpy. And so to go ahead and keep our constraints easier to work with, the enthalpy we're going to deal with under isobaric conditions, and the internal energy under isochoric, again, for kind of convenience of comparison. Now, what you may notice is that each of our three terms has a change in temperature term, so we're going to go ahead and just cancel that out. and substitute in our isobaric and isochoric heat capacity for our derivatives. And when we do this, what we find is that our isobaric heat capacity is going to be related to our isochoric heat capacity by essentially a linear deviation of n times r. So again, the number of moles times the ideal gas constant. However, we can also change from total heat capacities to molar heat capacities by just simply dividing each of these terms by n. And what we find here is that the molar heat capacity for an ideal gas, the isobaric molar heat capacity for an ideal gas is always going to be greater than the isochoric heat capacity by about R. So this means that our isobaric heat capacity is always going to be about 8 joules per mole Kelvin greater than our isochoric heat capacity. Now, this actually kind of leads to a question of, what does this mean and why do I care? And so what we see is there's going to be a difference in between these systems, because we can imagine treating a isobaric system as, say, I'm heating a pot of water, and the isochoric system as I'm heating a pot of water with a lid on. So if I'm, say, heating a sample with a lid on, well, it's going to reach temperature a lot more quickly. If you don't believe me, go ahead and microwave some food with a lid on and a lid off. Because as soon as I remove that lid, what I start having to deal with is the fact that as I'm heating the gas inside my container, it's going to start expanding. So I'm spending some of that energy that I'm inputting in as heat into PV work. It is literally expanding. And so that's going to be this origin of the reason why it always takes more heat, more energy, or more heat, or more time to heat a system with without a lid on top of it than it does without. And you can test this by putting a lid on your food in the microwave, or just boiling a pot of water with a lid on and a lid off. And you're always going to find, as soon as you put that lid on, you're going to an isochoric system, and it heats a lot faster because it requires less energy. And again, this extra energy is just due to that expansion against that constant atmospheric pressure. And again, I do want to emphasize that we did make an assumption of an ideal gas because we have this delta PV term that I was able to turn into an nRT. It is worth noting that as you move to, say, something like solids, what we see is that it turns out as you heat a solid, the pressure and the volume won't change that much, and my isobaric and isochoric heat capacities are going to become increasingly similar. So again, one of the things you should watch out for, well, this relationship holds very well for ideal gases. The more you move towards a condensed phase, like a liquid or a solid, the less well it's going to hold because of this pressure-volume relationship. However, as long as I'm talking about ideal gases, let's go ahead and use this as kind of a review of what we know about ideal gases. So if I have a monatomic ideal gas, we've already seen that it has a heat capacity of about 3/2 R. And that's because I have essentially 1/2 R dependence on temperature for every degree of freedom. And I've got 3 degrees of freedom because I've got 3 translational modes. So the isochoric heat capacity of, say, argon is going to be about 12.5 as long as it's ideal. However, the isobaric heat capacity has that extra R term due to the expansion of the gas when heated. So it's going to have an isobaric heat capacity of 20.8. And so you'll notice that if you're, say, heating a monatomic ideal gas, it's almost twice as hard to heat a ideal gas that's allowed to expand. We can also repeat this process for a diatomic ideal gas, where again, I have 5 degrees of freedom, 3 rotation, and or 2 rotation and 3 translation, which again gives me that same about 20 joules per mole Kelvin isocoric heat capacity. But as soon as I go to an isobaric system, I still have that extra R due to the expansion term. And now instead of, say, being almost twice as hard, it's about 50% harder to heat the system. And this is going to be a much more analogous to real situations, just due to the fact that oxygen and nitrogen, the primary components of an atmosphere, tend to be diatomic. You can also expand this process to a nonlinear gas, at which point you're going to have values of, you're going to have an isocoric heat capacity of 3 and an isobaric heat capacity of 4. Again, as long as it still behaves as ideal. And this is where we start running into issues, because it turns out that most systems aren't quite so ideal. So we have to deal with the fact that most heat capacities aren't going to follow these simple relationships. And one of the most important things we're going to end up running into is the fact that most of our heat capacities are usually going to have a temperature dependence. And we can go ahead and see this with things such as the internal energy. Because my internal energy is not going to have, say, a nice linear relationship with temperature. It tends to have some sort of curved relationship, and similarly for enthalpy. And because our heat capacity is more or less the first derivative of enthalpy with respect to temperature, we can think of it as the tangent to the line. And what you're going to notice is, say, at low temperatures, I'm going to tend to have much lower heat capacities than at high temperatures, where I have to tend to put in a lot more energy to kind of get the same bang for my buck. And we're going to kind of skip over these processes of why, as it has a lot to do with quantum mechanical behavior, and most specifically, the behavior of those vibrations as I heat them, and how much energy goes into the vibrations versus translations. As a quick summary, though, under low temperatures, more of the heat that I put in goes into translational motions, but the higher temperature I get, the more of that energy is going to go into vibrational motions. But in terms of trying to actually determine our heat capacities, well, we tend to have a very classic solution to these problems in a physics world. And that's if I don't have a simple linear expression, I go ahead and hit it with a power expansion. And the one that is most typically used is the Shamaty equation. So the Shamaty equation has a linear term, has a constant heat capacity corrected by a linear term, and then a quadratic term. So let's go ahead and try and break this down. So under most conditions, our linear term, or this constant value, is going to tend to dominate. And we see this with, say, something like helium, which tends to have a constant heat capacity because, well, it doesn't have a lot of IMFs and tends to behave about as ideal as anything ever will. However, as I start going over larger temperature ranges, we start seeing an increased influence of the linear correction. And you can start to see most of these graphs tend to have a certain constant slope to them. And that's really looking at this correction. And we tend to see the quadratic term start to play a lot larger roles as I go to larger temperature differences. And one of the things that's worth noting is that we're going to see this factor, so my linear factor, start to dominate under high temperatures, but really this term is going to almost dominate more under low factors. But it is worth noting that both of these temperature corrections are going to result in a net higher heat capacity than I would expect from a simple ideal system. So let's go ahead and see what this kind of looks like for our cases. So if I have an ideal gas like helium, my isobaric heat capacity is about a constant 20.8 joules per mole Kelvin. However, let's say I start having a little bit more IMFs and I get to something like nitrogen, which we go ahead and see here. So it turns out that nitrogen is going to be due to its nitrogen, is going to have kind of a uh, less significant temperature correction because it has these less severe IMF interactions and has a smaller size, which is going to again reflect in requiring a little bit less energy to make it go faster. And so we see this with its lower heat capacity as I go to higher temperatures. Now, oxygen under low temperature regimes is actually quite similar to nitrogen, as these two molecules look fairly similar. However, it has slightly larger IMFs, so it likes to stick a little bit more. And we see this in the B term. And this means that it takes me a little bit more energy to kind of make it split apart, as well as there's some difference in their vibrational modes, which again starts to shine a little bit more in oxygen. Now, ammonia, with its ability to make hydrogen bonds, is going to have both a higher base heat capacity, because I have to break these hydrogen bonds to make it move, and a higher linear correction and second order correction due to the fact that I have to break these sort of motions. However, it is worth noting that I am not just interested in how the heat capacity changes with temperature. In practice, what I really want to know is how the enthalpy itself actually changes over changes with temperature. And so in order to do this, I need to go ahead and make use of some integrals, because again, the change in enthalpy can be related to the integral of our isobaric heat capacity times temperature. And so using my Shimadi equation, I can substitute that in. And this is one of the major reasons we love linear expansions, is because I can break my integral up into parts. So instead of one big messy integral, I have three relatively simple integrals that I can solve in parts. And so my heat capacity has a nice, or my enthalpy has a nice simple linear relationship with temperature under small temperature regimes, small temperature changes, where I just have this constant A value. However, as soon as my temperature changes start deviating by, say, more than about 50 degrees, but certainly by the time you hit 100 degrees, then you start to need to worry about the linear correction term, which again is going to have a quadratic dependence on the difference of temperatures. Now, one of the things I want to make very clear is that what we're dealing with is the difference in between the squares, not the square of the difference, as this does occasionally get some people in trouble. And again, we also have our third correction term now being based on the difference of the inverse of temperature. And so what we tend to see in this case is that A is going to represent a lot of our traditional linear heat capacity, while as the B and C terms are going to tend to result in slightly higher enthalpies over larger temperature differences. So the larger my temperature differences are, the more these two subsequent terms are going to dominate my system. And we saw this again with our actual heat capacities. Now, in practice, how are you going to deal with measuring enthalpy changes and isobaric heat capacities? Well, this is typically done using a solution calorimeter. So you can think of a solution calorimeter as almost being the simpler cousin of a bomb calorimeter. Because in a bomb calorimeter, my system had to be completely separated from the surrounding system. I had to have constant volume, as well as adiabaticity. In this case, what I can do is have my system, whether it's, say, a um, an electrical source or a known reaction as a standardization for my calorimeter, like we used for the bomb calorimeter, whether it's something like a hot block of steel with a known heat capacity, or it could be some sort of chemical reaction that I actually want to monitor. So then I can look at how my system loses heat to the surroundings, and then I can leave it open to the surroundings because all I need to have is a constant pressure on my aqueous surroundings, which in turn will present a constant pressure on my system. Any sort of expansion of the system or my surroundings, I don't really have to watch out for. So then I can go ahead and relate the change in enthalpy of my system to the change in enthalpy of my surroundings. Due to the first law, these two should be the negative of each other. And then I can substitute in for the enthalpy of my surroundings, the heat capacity of my calorimeter times the change in temperature. So one of the things you should make note of is that the heat capacity of my calorimeter usually first includes the heat capacity of my water, but it may also include, say, how much energy it takes to warm the calorimeter around it, or any sort of non-ideality in the adiabaticity of the calorimeter itself. So there's a lot of extra factors that can go into the heat capacity of the calorimeter. So in general, we're often hoping that the heat capacity of the calorimeter stays relatively constant. And this often means trying to keep each of our experiments as similar as possible in between, say, standardizing our heat capacity of our calorimeter and actually making our relevant measurements of the enthalpies of our systems. And again, you're going to notice that this is a lot easier to set up than a bomb calorimeter because I don't need to have sealed containers and I have to worry much less about my whole system exploding. And this is one of the major reasons why we like using enthalpy, is it's a lot easier to measure. And as we've seen previously, as long as we're working with relatively ideal behaving systems, I can usually be able to compare the enthalpy of my system and its change in internal energy simply based on a difference of R. So hopefully this helps. Next time, we're going to start working with non-ideality a little bit more. Until then, take care.